Thank you very much. Yeah, as you said, my name is Jonathan Feinberg. I kind of strong ties into the University of Oslo, since the Simula Center is, well, technically owned by the University of Oslo and a couple of other government institutions. Well, a little bit about myself. I'm part of a group called Computational Geoscience, which does very similar work to what you do at PGP. More specifically, we work with, well, our main goal is to make a four-dimensional lithosphere model, or a paleo model, which I'm being told is basically trying to model how the world works, or the Earth is built up over time. So we're basically trying to make a time-dependent model. Thereby, we have the four-dimensional, so basically the 3-axis plus time, which is basically the main goal of what we're doing. And as part of trying to build up this model, we're trying to do this through a numerical simulation. So basically, we solve basically complex equation using well, numerical solvers, which requires high computing performance. So a part of the work we do is basically trying to make efficient code and focus in on clusters. And in this case, we're trying to get a niche within GPUs, basically using the graphic processors. So basically, you can take any computer which has a graphic card and exploit it and get results that are pretty similar to what you would get with a full-scale cluster. So that's part two of what we're doing. And the new things that we're basically trying to aim in nowadays is to try to get an uncertainty quantification basically framework on top of this lithosphere model as well. So basically, all of these three things are linked in a way. Basically, we want to make the model, and then we use the high-performance computing to try to actually solve the problems. And now we're trying to add an extra dimension. So basically, we are going away from the four-dimensional lithosphere model and going into a five-dimensional lithosphere modeling. But we're still in kind of the beginning of going into the 5 dimensions. We're basically getting a good handle of the 4-dimension, but yeah. So I will try to basically give you a little focus on the uncertainty quantification, where we are here now with uncertainty quantification. I will start by giving you a little description of the problem, so you get a feeling of what we're talking about. Then I'm going to talk a little more about the inner works of probabilistic collocation method, why it's good and things like that, and just giving you a brief overview of basically the guts of the method. And at the end, I'm going to show you a numerical example with the code and show you how well it works compared to comparable methods. Okie dokie. Let's just start with a problem description here. Basically, what we get, as in a general sense, what we have is a model we try to model. Well, easy enough. In our case, we're trying to model how the Earth looks, well, underneath the surface. So basically, we do that with our numerical solver. And the numerical solver I've called U in this case. From my point of view, I only need to see this as a black box. As in, it's a function. I put in some variables into this black box, and out pumps out some values. The values I put into it, basically the parameters, is space, time. So basically, we're trying to evaluate over a certain domain. We might have some other known parameters. Basically, I summarize that as a vector called eta. So xt and eta is our known parameters. And this is the important part because of what the uncertain quantification is. We have some parameters, c in this case, that are uncertain. Basically, what I'm saying here is that we don't really know what they are. However, we have a lot of experts that can tell us that, well, we don't know what it is, but we can say something about it anyway. For example, we can say that it has about a certain value, but we are a little uncertain on kind of plus minus some value. Or maybe we can basically say we have a specific bound on it. It's not uncommon for certain parameters to have, for example, only meaningful if it's larger than 0. Things like that. This can be incorporated into probability. So basically, we interpret it, kind of expert opinion can be interpreted into probability density functions. And when we have that, then basically the idea is that we want to insert all of this into a solver and basically analyze what gets out on the other side. So we know the uncertainty on the model parameters. Now, let's find out what is the uncertainty of our model as a whole, as a function of the uncertain parameters that we put into it. So I make a distinction here between little u and large u. It's a very typical distinction that is made amongst probability theorists and statisticians, where u is the unrealized value. Basically, it has a set of potential values, while the large u is basically the evaluation that comes out. So basically, for every combination of x, t, c, and eta, you get one large u. However, u is the function that can be any potential value. So we're basically talking about the difference between what could be and what is.
How do we choose the probability model?
Huh?
How do we choose the probability model?
Well, for the c parameters?
Yes.
Well, that again basically is done through expert opinions. So basically well, at least in CompG, or CG as we call it locally, we basically have a lot of people that are experts in geology, geophysics, etc., etc. We even have people at Statoil helping us basically map out, saying how things behave. They really basically set the parameters for the probability density function for the random variables. And if we really don't know, we just use some kind of naive uniform interval saying that it's between 2 points, and we still get decent result out of it.
So you're assuming a distribution without any broad tail?
For the most part, yes. However, the probability framework basically has this natural connection between certain type of random variables and as a phenomena that we find in reality and certain probability density functions. So basically, if you're counting a set of variables that we are interested in the sum of something, then we will instantly assume from a probability standpoint that this will be normally distributed, which we know has a not very heavy tail. But waiting times, for example, we're waiting until something will occur, and we know it happens with a rate of things. Then we'd usually have an exponential distribution. An exponential has a heavy tail, in a sense. So it's very often where you get to a situation like, well, this is a physical phenomena, it has this behavior, well, then we can use this density function, which naturally just matches well with the problem you're trying to describe, often. Okay, just a little teaser into how easy uncertainty quantification should be. This is code that actually works. Basically, we need some kind of solver. This is written in Python, fairly similar to MATLAB. So if you know one or the other, then you should be able to read what's going on here. Well, first of all, I define a function. The first parameter is basically a vector of your uncertain parameters. Basically what I do, I split it up into the two parameters of interest, c and I, and basically kind of put it into this really simple formula over there, which basically is the solution of the world's simplest ordinary differential equation. But in reality, you would put really heavy code inside of this, basically a function called to some kind of solver that you would use, or I would use in the sense. Locally at Simula, we would use the Phoenix project, for example, which is a finite element model that basically can do this and basically extract out values from that and return variables of interest from the Phoenix model. Then I define my uncertain parameters. I don't go into details of why I chose these specific distributions. However, I just did because, well, they look nice and they're different from each other. So uniform density function between 2 and 10. And a normal distribution defined at the mean 2 and the standard deviation 2. So basically think of this as we're expecting it to be 2, but with an error margin of 2. So from 0 to 4 in a sense. Then I join them together with a joint operator. I call the method called PCM, which is a part of the PC package. It's a polycal package. Define some parameter. I'm going into the detail of what that parameter should be later. And basically, it says that it only took 12 evaluation. And that basically means that it doesn't really require that many evaluation to get decent results, which is kind of the magic of this PCM method. That if your code is really slow, if it takes hours, if it takes days to evaluate one run with one set of parameters. You don't want to be running this thousands of times to get something out. So basically the beauty of this method is that you don't really need that many evaluations. And basically when you have your result out, you can do some standard probability analysis on it. It's basically a toolbox, a function that can say something about how uncertain the variable you got out. The two most typical analysis tool you use in probability theory is the expected value, which basically says what typically will it end up to be. And the other one that basically is maybe even more important is the variance function that basically says how uncertain are we, as in on how big an interval do we need to basically assume this result to be on. If that interval is really small, then we get a stable solution and we're good to go. However, if the variance is really big, that means that our solution is really unstable, and just changing our parameters a little bit within where we think our parameter should be, you will get a completely different answer, and we don't want that. However, if you can't get that, well, at least this will tell you this. So you can use this as a sensitivity analysis, in a sense. Okay, a little bit about the competing method. Anybody who has done uncertainty quantification within any type of modeling knows about a method called Monte Carlo. Monte Carlo is used, it's kind of been used heavily since the 1950s. And the reason for it is very simple to construct, and very relatively easy to construct. Basically what you do is you create some synthetic samples. That's kind of the beauty of probability theory, is that if you have the probability density function, then you can use that to create random variables. And basically what we do is we generate a lot of them. And for each of these random variable, or vector if you have many of them, you insert those into your solver and generate some output data. So basically we are generating a random vector, inserting it into a solver, and generating a sample. And then we're repeating this many times. And when we have a lot of samples, then we can analyze those data as if it was an approximation of the model you're trying to analyze. And this is, even though we basically use a lot of word on it, it's not really hard, because you basically look at your solver as a black box. You don't really need to know anything about it. Also, it's basically applicable to any type of model. It doesn't even need to be continuous or smooth. It doesn't make any assumption of how it actually looks inside the model. It also scales really, really well in the number of dimensions, in the sense that if you have hundreds or 200 number of unknown parameters, it still performs well in the sense that it scales linearly with the number of dimensions. And Monte Carlo simulation is actually unique in that sense, even today, as no method can compete with Monte Carlo when it comes to scalability. However, the problem with Monte Carlo simulation is that it converges really slowly. You need 10,000, 100,000, even 1 million samples sometimes to even get decent accuracy on your results. The reason for that is that we're dealing with random variables. If you run the same code twice, you will get 2 different answers. And the problem here is that you don't really want a solution that will differ every time you run the same code twice. So to compensate for this instability, what it does, it basically averages out over a lot of samples. So basically exploit the fact that you need a lot of samples to get a stable solution. And the more sample you have, the more stable your solution becomes. So in a sense, you can never actually reproduce a Monte Carlo simulation without basically fixing your random seed in a sense. But yeah, as a repeatable code, it's hard to get stable solutions without generating a lot of samples. And coming back to the idea of having costly numerical solvers, you can't afford to get up to the required number of samples. Okay, let's try something else. Let's do something completely different. So, new idea. Let's just take the numerical solver of interest and approximate it. And what better way of approximating than through a polynomial? This is something that we've been taught since early calculus, is that any function can be approximated with a polynomial. You can think Taylor, Maclaurin, or Lagrange polynomial. It doesn't really matter. the general formulation is that you create a sum of Fourier coefficients multiplied by some kind of polynomials. So basically, the polynomial is given, and the coefficient has to be calculated. But in general form, that's what you have. So why we want to do that? Well, if you have this this approximation of your true model, then doing analysis is cheap, or even free in some cases. Since, well, we're talking about polynomial, and you're only trying to deal with the random variable within C. And notice here that the x, the t, the eta is moved into the coefficients. So all you have to deal with is the actual polynomial when you're doing uncertainty quantification. You also have the possibility of scale the accuracy of your model, well, at least in theory, that the more polynomial terms you have, the more accurate your model becomes. The assumption made in this kind of build-up here is that, well, the only assumption you need to make for it to get decent results is that your solver needs to be smooth in the parameters that are random. So basically what I'm saying here is that the CI coefficients, the Fourier coefficients, they don't really need to be smooth. They can be discontinuous. They don't even need to be basically continuous over any part of the domain. They can have any type of behavior. The only thing we're assuming is that the polynomials that we're approximating with are smooth, which is a smaller assumption than assuming the whole model as smooth. And if we can, was there a question? Heard? No. Okay. And if we have basically used this model instead of the real model, then we basically reduce the problem of trying to do uncertainty quantification to finding the coefficients. Because if you have this formulation, as I said, it's easy to do the analysis. Okay, now we're going a little more into the guts of polynomials chaos theory. And it's about selecting polynomials. We could use Lagrangian polynomials. We could use Taylor polynomials. But let's instead use something that makes a little more sense within the probability framework. Now, what you see here is that we have reformulated the idea of inner products. So basically, we take something from functional analysis, or even kind of linear algebra, if you consider f and g as vectors. But in this case, we're considering f and g as functions. But we're defining it within a probability framework. So we have something from functional analysis, we have something from probability analysis, and we bring them together through this definition here. So we're basically defining the inner product between two functions as the expected value of the multiplication of those two functions. And the polynomial we want to choose for this analysis is that we want them all to be orthogonal. So basically, if you take the inner product of two different polynomials, you want it to be 0. Yeah. Why would we want to do this? Well, we can show with a little bit of mathematics. I'm not going into the details of it, but the idea is that the approximation you get will be optimal. This type of optimality is not very uncommon to see within normal functional analysis, that basically error get minimized. But since we basically linked our expected value into this definition, then basically with a little bit of mathematics, we can show that the uncertainty, basically the variance, which is basically the probabilistic way of saying how uncertain things are, it's minimized. So basically, we get the best result and the best approximation we can get by choosing our polynomials to be orthogonal on the functional space defined by that inner product and norm. Okay, so we have chosen some good polynomials. However, they need to be customized for each problem in a sense. If you change the probability distribution, or just change the parameter of probability distribution, in the sense that, for example, if you've chosen a uniform distribution between 0 and 2, and now you want it to be 0 and 3, then basically the polynomials you had for the first case will not be orthogonal for the second case. So for each problem you get, you need to redefine the orthogonality, in a sense. So basically, you tailor a polynomial, not as in Taylor polynomial, but you tailor a polynomial for the problem at hand. And to do that, it's not really that hard because we have the Gram-Schmidt's method. A simple way of taking random variables, even dependent ones, and just generating an orthogonal basis from an independent one. Okay, we have our polynomial. Now we want to calculate our coefficients. There are more than one way of doing it. For this toolbox, I use a black box method ID. Basically what we do is we select some collocation nodes. Some nodes basically spread out throughout our domain that we want to evaluate for. And when we say domain, I mean the domain of the uncertain parameter xi. Time t and spatial coordinate x is implicit in this case here. We are just reducing this just to look at the uncertain parameters. Then when we have these collocation nodes, we evaluate both all the polynomials and the solver for these collocation nodes. This is basically what takes the most time of the whole solver, is that you basically need to evaluate your function at a certain number of collocation nodes. When you have this solution ready, then all you need to do to find your coefficients is to do some kind of linear least square approximation. Very straightforward. There are standard packages for doing it, so that part is not very complicated. However, I just said that we need some collocation node, but we should be thinking about which collocation node is the best one to select. We have some kind of different priorities that we want to incorporate into the same model. On one hand, we basically want to cover a whole domain. So basically, if we can get our nodes be spread out throughout our whole domain, that would be a good thing, because then basically we get representation for the whole domain. On the other end, we also have a situation where basically we want to only represent the high probability, because low probability is basically equivalent with irrelevant. So we want to have a higher number of collocation where the probability is high. And kind of the last thing we basically need to keep in mind is that we want the collocation number to be low. Is that we can't afford to evaluate the solver too many times. So basically, let's keep it to a minimum. So how do we do that? Well, there are more than one way of doing it. Just the general way of how I do it. Basically, what I do is that I create some samples on a unit hypercube. And basically, what method I use to spread my points over the unit hypercube. Sorry. Can be, well, you can sample just the regular grid, but makes more sense to use some kind of sparse grid. So basically, some ID that will get you fewer points per dimensions than any type of other grid. When you have basically sampled everything on the unit hypercube, then what you do is you use a probability theory type of operator to map all the samples to the distribution you're interested in modeling for. So again, we're tailoring the collocation nodes to the probability density that we're trying to do analysis on. And here we have an example of bivariate normal distribution with the correlation coefficients, and see basically how the collocation node perfectly align over the area where the probability is high, spread out. Right. That's correct. They are deterministic. So basically, if you run my code twice, you will get exactly the same results. If you do that in Monte Carlo, you will not. Returning to the code example, I'm using a little different example there, but it's still the same idea here. You have some numerical function that evaluates over a certain domain, in this case, the time domain. We have two uncertain parameters, c and I, that defines the uncertain domain. I define them to be uniform and normal as before. I then do two analyses in this case. I basically defined a polynomial with defined t for 0.5. Basically, I'm only doing one polynomial. And for q, I'm defining it for the whole time domain. So 100 values. So basically a vectorized polynomial. So the coefficients are now vectors. Okay, and the reason I'm doing that is because I'm going to go in a little more detail on the P before I go in a little on the detail on the Q, which I'm doing two different type of analysis of. Well, this is the P. What I've done is just simply round it off. My toolbox has a set of tools that let you analyze your polynomial result from your PCM method. This one basically just reduces the number of relevant coefficients so I can print it out in a way that actually looks good. And it behaves in a polynomial very close to any other type of polynomial package that you're used to. For example, you can evaluate your polynomial if you're interested in it. It is an approximation of your model, of your solver, so you can do whatever you want with it. However, as we mentioned before, what is specialized to do is uncertainty quantification. So of course, the toolbox includes all that you need to do the uncertainty quantification, the expected value, variance, covariance, etc., everything that you need. That's a little bit about the P. Now let's look at the Q. Here what I've done is compare the the probabilistic collocation method with the Monte Carlo method. What I've done is I've chosen my parameters to be 2, so a polynomial of order 2, 3, 4, and 5. The method then basically calculates how many collocation nodes it requires. In this case, 5, 17, 49, and 129. And for comparisons, I've done the same thing for the Monte Carlo method. I've created 5, 17, 49, and 129 samples, and then done an analysis finding out how well does it do to actually analyze the expected value of the model. So on the y-axis here, it's the absolute difference between the expected value of the real model, which I've calculated by hand, and the approximation, which is done by the two methods here, Monte Carlo and PCM. And as you can see, the PCM method does it really much better than the Monte Carlo method, by an order of magnitude better. And not only that, if you look at the Monte Carlo results, you can see that the result isn't really stable. For example, if you look at the 49 samples, the red line, that one is lower than the teal line, which is 129 points, in the sense that you can't really trust your results as much, because if you run the code twice, you will get different results. 10,000, 100,000 is actually, there is no good answer to that question. It's a little more doing like this, but usually you talk about on the scale of 10 to the power of 5, 7, or even higher than that, dependent on the complexity of your problem. It depends really on what kind of probability function you're trying to sample over. Yeah, well, that shows you how well the PCM method can work. With bootstrapping? Yeah. As in, well, bootstrapping comes in two versions, parametric and non-parametric. Parametric bootstrapping is forward Monte Carlo simulation. This is parametric bootstrapping. It's just a different name for it. On-parametric bootstrapping is not something I've actually done, but parametric bootstrapping is more typical in a situation where you have data, because doing the reparameterization of the data allows you to do analysis without actually having the probability density function lying underneath. So basically you want to resample old samples. In this case, we don't actually have any data. If the input on certain parameters that you're trying to model actually have some data, and it's a limited set of data, then of course resampling makes a lot of sense. This is not the intended use of this package, but it shouldn't be that hard to actually create something that will work as a resampling, as an input instead of the density function is samples, and just resample from that set of samples. Shouldn't take me that long at all. If you're interested, I can actually make it. It should take me about it should take me half an hour or so. It's not that complicated. Okay, just to conclude, ignore the picture in the sense I didn't find a good conclusion pictures, but I'll just have some funny thing, I thought. Well, the good thing about PCM method is it's easy to set up, especially when I have it as a black box. You don't really need to know what's going on underneath the hood. You only need to set the order of the polynomial. You don't have that many assumptions. You only assume that the parameter space is smooth, not your space or time domain. It converges really, really fast because it uses some smart mathematical underlying kind of IDs that makes it fast. And you get this nice functional representation of your problem. It's like for this time at this time space location, it will have, you basically get a link between the input random variables and the output random variable as a function, as a polynomial function, which is much prettier to look at than just a set of data samples that Monte Carlo gives you. Okay, thank you for your attention. If you're interested in actually using this type of code, it is available on Bitbucket for free. It's open source, of course, as science community often are. And yeah, that's it.